السلام عليكم ورحمة الله وبركاته. يعطيكم العافية شباب وصبايا. Today we'll talk about fluid mechanics part 4 from chapter 13, which is all about Archimedes principle. At the beginning, let me take this container filled with a certain fluid or liquid, for example, water, and the density for this fluid is denoted by rho sub f. And as you can see here, I have an object of density denoted by rho 0 or rho naught. Now, what's going to happen if I dropped or if the object immersed in the water? We have two scenarios, and these two scenarios depend on the density of the object compared to the density of the fluid. Therefore, the first scenario, if the density of the object is less than the density of the fluid, I'll have floating object. Second scenario, if the density of the object is greater than the density of the fluid, I will have totally submerged object. In principle, we can tell the following. Archimedes' principle states that a body partially or totally submerged in a fluid is pulled upward a force, and this force is equal in magnitude and opposite in direction to the weight of the displaced fluid. As you can see here, what Archimedes said is the following. Let me summarize the previous slide. Archimedes said the following: the point force on something is equal to the weight of the displaced fluid. Therefore, this statement can lead us to the following question: what is the point force, and what is the weight of the displaced fluid? Let me take the following container. As you can see here, I have my container, and this container is filled with a certain fluid, and the density of this fluid denoted by rho f or rho sub f. Now, if the object is totally submerged in the fluid, I will see the following. First of all, we will have a displaced fluid, as you can see here, and this displaced fluid has a volume equal to the volume of the whole object. So I can say V, or the displaced fluid volume, equals to the volume of the whole object. This is number one. Number two, this object will experience two different pressure, one from the top and one from the bottom. Therefore, we have two exerted forces up to now, two exerted forces acting on this object. The exert or the force or the top force due to the top pressure, and the bottom force due to the bottom pressure. Now, from here, since the bottom pressure is greater than the top pressure, we can say the point force is equal the force due to the bottom pressure minus the force due to the top pressure. Now, we can use the definition of the pressure, whereas the pressure is force divided by area. Therefore, the force can be evaluated as F equal the pressure times area. Now, you can see here the area for the subject, for the object, is a common. So we can say the point force equals the change in pressure times area, whereas the change in the pressure back to the I think Chapter 13, Part 3, to the pressure variation with the depth, we can say here delta P equals rho of the fluid times the gravity times delta H, whereas delta H is H2 minus H1, which is H, the height of the object, times the area. But be careful, the height of the object times the area or the cross-sectional area of the object is the volume. And as I mentioned before, the volume of the object is the same as the displaced fluid volume. Now, from the previous two slides, we can say the following. In the totally submerged scenario, the density of the object is greater than the density of the fluid, and the volume of the object is the same as the volume of the displaced fluid. What will happen if I attached my object to the end of rod and immersed it totally in a certain fluid? I will have the following forces: the tension directed upward, the weight of the object directed downward, and the point force directed upward. Now, using Newton's second law in equilibrium case, because here we are talking about equilibrium. So summation F equals 0. We have tension plus point force equals W naught. Now, solve this equation in order to calculate the tension. The tension will be W naught minus B. But we know W naught is mass, or the object mass, times the gravity. W is raw fluid times VD times G. Whereas the mass of the object is the density of the object times the volume of the object, which is the same as the displaced fluid. Take the displaced fluid volume and the gravity constant as a common, you will get this important formula. First example, I have a block of a mass 6 kilograms and density of 1200 kilograms per meter square cube is immersed totally in water. Okay, first of all, we have to know that we are dealing with Archimedes principle in the case of totally submerged. This is number one. Number two, this 6 kilogram and this 1200 kilogram per meter cube, those are the mass and the density of the object. Determine the block's weight or the object weight. We know the weight is m naught times g. We have the mass and we have the gravity. What is the buoyant force? The buoyant force is rho fluid times B, or V sub D times G. We know the density of the fluid, which is for water, and the gravity, which is known too, but the displaced volume is unknown. Now, go back to the question. You can see the key from here. Mass of the object and density of the object. We can use it to calculate the whole volume. Whereas the whole volume, V or V naught, is the same as the displaced fluid. Now, we have V, we know rho, and we have G. Simply plug the numbers, you will get the buoyant force. Second example, as shown, what is the buoyant force? Okay. Let me take a breath. In this example, which is something I do like it, okay? The question here is asking me to calculate the buoyant force. And we know the buoyant force B equals rho sub F, or the density of the fluid, times the displaced fluid volume, times the gravity. Now, the density is known, gravity is known, but the volume of the object is unknown. We have no idea or no key for the volume of the object. Now, we can go to the second formula of the point force using the tension, as you can see here. I have tension upward, point force upward, and the weight downward. So easy, we can say tension plus B equals W naught. Therefore, B will be W naught minus T2. As you can see here, B equal W naught minus T2. T2 is known, which is 12 Newton, but W naught is unknown. Now we can go back to the first graph or the first diagram. As you can see here, tension upward, weight downward. Therefore, T1 minus W naught equals 0. From here, we can calculate W naught and easy plug it back into this formula to get the point force. As a homework or practice, what is the density of the object? You know the point force, and we know the weight of the object. So you can use this to calculate the density of the object and the volume of the object too. Third example, a cubic box of length side of 50 millimeter is totally submerged in a certain fluid. Okay, we are talking about Archimedes principle, and the object is totally submerged. Here I have the length side for the object or for the cubic box. Therefore, I can use this to calculate the volume of the box in case if I need it. If 2000 Newton is the lost weight, what is the liquid density? How to think about this example or this problem? The liquid density, rho sub F. We know that the point force equals rho sub F times V sub D times G. Okay, we know from here the point force. Therefore, we can say the density of the liquid or the fluid equals B divided by V and G. B is known, G is constant, but the volume or the displaced fluid volume, how to calculate it? Now, we are talking about total submerged. That means the whole volume of the object is same as the volume of the displaced fluid. As you can see here, we calculated the volume of the displaced fluid or the volume of the whole object. Now plug it back into rho sub F or the fluid density to get this one. Second case or the second scenario, when the object is floating, which means the density of the object is less than the density of the fluid. Let me go back to my container with rho or density of the fluid. Now, let us immerse the object, but be careful. The density of the object is less than the density of the fluid. Therefore, the object will be something like this, floating, and we do care about the submerged part of the object, or in other words, we are talking about the part of the object below the surface of the fluid. I will call it V sub S, or the volume of the submerged part of the object. Now, you can see here the displaced fluid, whereas the displaced fluid is the same as the volume of the submerged part of the object. Now I have two forces acting on my system or on my object, the weight and the tension, and both of them are equal in magnitude and opposite in direction to keep this system in equilibrium, or this object in equilibrium. And be careful, one more thing, be careful that the volume of the volume of the displaced fluid, or the volume of this V sub S, all the time less than the whole volume. Now, as I mentioned, I have two forces, and we are talking about how can I say it? We are talking about equilibrium. Therefore, net forces equal 0. So the point force minus W naught, and I'm sorry, here this is not in scale. This vector of the W naught should be same as the magnitude, or yeah, in magnitude of B. Therefore, B equals W naught. Substitute the value of B, and W naught, you will get rho of the fluid times the volume of the submerged part of the object times the gravity equals rho naught for the fluid times the volume of the object times the gravity. We can cancel out the gravity with the gravity. We will get rho sub F V sub S equals rho naught times the whole volume. Another example, or the first example for in this subject, an object is floating in a water. If 60% of this object or this volume is above the water, we do not care about what is above the water. We do care about the part, or the submerged part in the water. So in other words, we have 40% of the volume inside or below the surface. What is the ratio of the water density to the object density? We know this in case of the floating object, and we can say the density of the water, or the water density divided by the object density, will be the whole volume divided by the submerged volume of the object, or the displaced volume. Now, 60% is above, that means 40% is below. Therefore, we can say the volume of the subject, the submerged part is 0.4 of the whole volume. Take this one, put it back, you will get the density of the water divided by the density of the object equals to 2.5. Last example, a body floats in water with 1/4 of its volume below the surface of water. Here, this something like a key. The volume, the displaced volume is equal 0.25, or 1/4 of the whole volume. Determine the body density. Okay, we know this formula for the partially or floating object, and the density of the body from here will be rho naught equal the fluid density times V sub S, or the displaced fluid, divided by the whole volume. But we know the displaced fluid is equal 1/4 times the whole volume. Take this one, put it back, you will get the density of the object equals 250 kilogram per meter cube. Thank you, and see you in the next part.